Well, good afternoon, everybody. I'm glad you're all here. We spent a lot of time talking about the nitrogen and the phosphorus in manure, but the fact is there are a number of other materials that are in it, and there are some impacts of manure on the soil system that others might be talking about, not necessarily nutrient management planning folks. And I thought it would be a good idea if we were at least aware of these issues so that we weren't totally in the dark if someone started talking about it or we read an article about it in the paper or in the ag press. So today's conversation is going to be about the non-nutrient aspects of manure utilization. And again, I'm going to talk about 3 or 4 aspects of it, and then Dr. Yankos is going to give you his presentation on one very specific aspect of manure utilization that he's spent a number of years researching. So I'm going to talk first about the organic carbon in the manure, and it has impact on the biological, physical, and to a lesser extent, the chemical properties of the soil. Then I'm going to talk a little bit about greenhouse gas production, which you may never have thought about in terms of manure utilization. That's been on the radar screen for probably 10 or 15 years. Then I'll go and talk about the presence of disease prevention or disease treating compounds that are often in animal manures. And from there I'll go to the residuals from crop protection chemicals that are used in feed production that can show up in manure also. So it's a very broad look at a number of aspects of manure utilization that have nothing to do specifically with nutrients. Okay, well, first of all, let's realize that manure is a very heterogeneous material. It contains the metabolic waste of the animal. That would be the waste from our kidneys, for example. And in the case of mammals, that material is going to be urea. In the case of birds, that will be uric acid. But the urine or the metabolic waste of an animal also contains a whole array of other soluble materials that the organism is ridding itself of also. And the feces also is a pretty heterogeneous material. It contains some food that wasn't digested. It also contains microbes from the intestinal tract. And in the case of animals, sometimes the microbes can be human pathogens. It also contains cell wall debris from the animal gut. So there's a wide array of solid materials that exist in the feces. And then either in the feces or the urine, there can be various things that the animal was fed to promote growth. We'll just lump them together as growth-promoting substances or chemicals in the feed, depending upon how you might see this. And then the animal, of course, is growing and maturing. So some of these growth hormones, these hormones that the animal is producing, are also going to show up in either the feces or the urine. So we're going to touch on all of these in the 2 hours today, although Dr. Yankos is really going to spend time talking about the hormones. I'm going to leave that to him. So let's talk first about the organic carbon. The organic carbon additions with manure are in the same ballpark or order of magnitude as what we might get from crop residue. So what I've indicated here is that typically in about a 2-ton application of poultry litter, we're also getting about 3/4 of a ton of organic carbon. Whereas in a 20-ton dairy manure application, we're getting a little over 3 tons of organic carbon. Now compare that to what you get from the corn stover that's left when you harvest corn grain, and we're looking here at about 170 bushels per acre yield goal. We're getting about 1.3 tons of organic carbon then. Now these are all based on some average values and some assumptions on my part, so they're definitely very ballpark figures. But in fact, you can see that there's not a huge difference between these. There's not a 10x or 50x or 100x differences. They're in what I would call the same ballpark. Now I do want to emphasize that more than the tonnage of stuff, and we'll talk about this more when we look at a diagram, these aren't necessarily equal in terms of how the microbes are going to see them, all right? We're just saying that in terms of the weight of organic carbon that might be added to a soil in a typical manure application or in a typical crop residue, that the amounts are in the same ballpark. Right. So what are the effects of adding organic carbon in 3/4 of a ton or 3 tons or 5 tons per acre? Well, as we talked about last month in the cover crop webinar that we had, there's this cascading series of things that happen when you add organic carbon into the soil. First of all, you stimulate biological activity because the microbes are said to exist in what's considered to be a rather semi-starvation state. So if you put some organic carbon in there, this is an incredibly accessible energy source. This is how they get their energy, breaking down carbon-carbon bonds. You're going to stimulate microbial growth. You probably also have a crop growing in that soil, and both the crops and the microbes exude binding agents. Some authors call them mucilages or gums, and some people actually call them cementing agents. So you're cranking up activity and you're causing the production of materials that are going to cause soil particles to stick together. Thus, step 3 here would be you're going to get an increase in aggregates in soil clumps of particles, especially the larger sized ones, and that's going to improve soil structure. It's also going to make your soil more friable and softer if you're trying to break it. Now when you start looking at some actual things that are commonly measured in a soil, you'll see that with long-term applications of organic carbon, you start to actually see decreases in bulk density and an increase in pore space. And that's usually accompanied by an increase in the infiltration rate, or the rate at which rainwater or irrigation would enter into that soil, and the hydraulic conductivity, which is the rate at which liquids would move through the soil. And overall, kind of as a summary, we could say that adding organic carbon, particularly routinely and year after year, is going to improve your soil tilth or your soil quality. So just as we said these things were true about growing cover crops or green manures, it's also true about manure application, particularly long-term manure application. So let's review this diagram again because I think there's a lot in it we can learn about. And Heather. Okay, well, let's look at the top diagram first. This is the graph that shows both the carbon dioxide evolution and essentially the number of organisms that exist after you apply a fresh residue to a soil. And you can see here that there's an incredible increase in growth with a subsequent drop-off of both the carbon dioxide that would be given off and the number of organisms that you could count if you were to culture them or find a way to measure them, right? So the microbes increase in number, they reproduce, each one of them is respiring, and so this curve pretty much mimics both of those things. Now if you look down here at what's happening with the material in the soil that are in existence, you'll see that first of all there's some humus that was already in the soil, of course, and you're also adding some new things. So first of all, let's talk about what happens to the new things. Well, again, as the microbes start to grow, they're consuming these. So the amount of material from the original tissue drops off with time. This is true of manure just like it's true of cover crops or green manures. And as the microbes start to work on that material, they make new stuff. They synthesize stuff. The gums, the mucilages, and other things that might not have a particularly strong binding effect. So as time goes on, they're making materials, but eventually those materials also are probably going to get used as energy sources. So the levels of that will drop too. Again, with time, you're going to see an increase in the amount of humus in the soil compared to what was there before. Now let me stop for just a moment and say that how much humus you're going to get, increase in humus, you're going to get is really very much a function of what material you put into that soil. If you put in a very labile, highly digestible material like a fresh manure or like a cover crop that has a narrow carbon-nitrogen ratio, you're not going to see much of an increase in humus for a substantial amount of time, perhaps many, many years. Whereas if you add crop residue or a more mature crop that has more structural carbohydrates in it, you're going to get more of an increase in humus. So this is a very generalized diagram, but I want to say that to show this amount of humus increase over a short period of time, the author was probably assuming that it was more like crop residue with lots of structural carbohydrates and more resistant compounds than a fresh manure or a green manure. I also want to point out this priming effect here because many people have found this. You notice that the amount of humus in your soil actually drops for a while as your microbes are undergoing that rapid growth where they're attacking the new materials that have been added to the soil. And what we believe is that while they're attacking those materials, they also attack some stuff that they were pretty much leaving alone before the new additions occurred, right? And I will say that as I was going through the literature, both for manure applications long-term and for the cover crops that we talked about last month, there were actually studies where people said that they didn't see any increase in the humus over time due to what they were applying, and they actually thought that the organic matter might have been decreased a bit by adding these fresh, very digestible materials. Okay? But certainly for long-term, we tend to see some increases. Okay, so one of the things, again, that we see when we add a material is an increase in microbial biomass. So here's a study from Alabama where they looked at the effect of 10 years of poultry litter on the Decatur silt loam soil. And they compared that to comparable rates of commercial fertilizer, both in the nitrogen, the phosphate, and the potash that went on with the poultry litter. So this is relatively long-term as long-term studies go. And I want to say that microbial biomass, as they measured it, and as a number of other people measure it, is a pretty gross indication of the carbon or the nitrogen coming from the microbial tissue itself. And essentially what they do is select a chemical extractant, often a weak acid, that they believe extracts the organic nitrogen or the organic carbon in a soil, and then they kill the microbes. Sometimes this is done with a microwave treatment, and sometimes this is done by using chloroform. But at any rate, they try to kill the microbes, they let the soil sit for a while, and then they come back and extract it again. So this is a very gross measurement of what's believed to be associated with microbial biomass. And in this case, we're looking at the microbial biomass nitrogen from the commercial fertilizer treatment and from the poultry litter treatment. And you can see that in terms of pounds of microbial biomass nitrogen at the end of 10 years of these treatments, there was far more than there was microbial biomass in the commercial fertilizer treatments that had gotten the same amount of NP and K. Right? So here's a pretty good indication, a measurement actually, of the effect of 10 years of poultry litter on microbial biomass. Now another thing they looked at, and I've tried not to talk too much about nutrients, but a number of authors, a number of scientists have decided that if we could look at a more labile measurement of organic carbon or organic nitrogen, we'd be better off in terms of predicting the availability of material that's already in the soil. And so these folks also looked at particulate organic nitrogen. Now this is interesting because it's now believed to be a pretty good measure of what's going to be available to the microbes over the short term. And it's basically coarse-sized, undecomposed organic nitrogen. And essentially you screen your soil through a 0.53 millimeter screen, and then you determine how much carbon or nitrogen are in that. All right? So you can see that they were able to pick up a real difference in terms of the particulate organic nitrogen, what we might consider to be the potentially mineralizable organic nitrogen in the poultry litter treatment that was not obvious in the commercial fertilizer treatment, where the only organic contributions would have been from the crop residue. So again, it kind of reinforces the idea that this might be a useful measurement to incorporate into soil testing down the road if we want to estimate our potentially mineralizable nitrogen pool from what's already in the soil, not from what we're adding as manure, but from what's already in the soil. Okay, another way to look at what's going on with our microbes is to actually look at the genetics. And there's some very high-powered tools that have become available in the past 15 to 20 years. And the group at North Carolina State, led by Dr. Liu, have looked at a study relating to that. So they basically extracted the genes in the soil. And they looked at several organic amendments, not just manure, but there were others. And this happened to be on the Orangeburg sandy loam. So they treated the soils both with litter and with other organic sources, and they looked at things like the diversity and the richness of the soil organisms across those treatments. And what they found was that the treatments that had gotten organic nutrient sources as opposed to commercial nitrogen and commercial NPK were much more diverse and rich. And what this essentially means is that there's a far greater array of types of organisms as well as a larger number of those organisms. So there's different genes representing different organisms, and there's also higher levels of the genetic expression or a greater number of each of those genes. So again, at a very powerful, essential look, we can see that by adding organic nutrient sources, we can enrich the microbial a network in our soil. And the bottom line is that if you have more types of organisms and a greater number of those organisms, your soil has a better ability to break down a wider array of the stuff you might put on it, and for those organisms to use that material as an energy and a food source. So we're really cranking up the biological activity of our soil. Okay, now another, and again, this is a very crude way. We've been able to measure soil respiration for a long, long time. Essentially, you put a little beaker and you trap your carbon dioxide evolution. This has been done since the early 1900s. And in this particular study, they put on equivalent amounts of PAN in commercial fertilizer and organic treatments. This was a long-term experiment. And in August of year 5 and 6, they went back and measured carbon dioxide evolution in the treatment that had gotten ammonium nitrate, in the treatment that had gotten poultry litter, and in the treatment that had gotten the green manure of vetch and rye. And even in August, even though the materials were put on in mid-May, you could still see more biological activity in the green manure compared to the ammonium nitrate, and the poultry manure was the highest of all. So this biological activity is not just an immediate thing. The effect is seen for quite a while after the materials are actually applied to the soil. Okay. Now, in terms of what happens when we add a crop residue or a manure to a soil, this is a beautiful illustration, and this came out of a publication of Haynes and Nadeau back in Nutrient Cycle and the Agro-Ecosystem back in 1998, but this does a wonderful job of telling us. We add manure, we add crop residue. Well, what happens? Well, the organic matter starts to decay. We have an increase in microbial action. They start producing these polysaccharide mucilages, and they start binding particles together, and we get improved structure, all right? And it leads long-term to an increase in organic matter, and that's going to lead to an increase in porosity. And an increase in organic matter is going to stimulate earthworm activity too, not just microbes. So we get all their castings and all the stuff they pass through their system. And in fact, it's this incredible, complicated interrelay of stuff that long-term means we have improved soil structure. You know, we have more macropore space. It's going to take in water better, faster when it rains. Our soil is going to be more friable. It's not going to have such high strength, and our roots are going to be able to penetrate it better. It's just this long-term overall positive effect of adding an organic carbon source in terms of our soil structure. Okay, so one way people look at soil structure is to look at something called aggregate stability. And there's a variety of methods out there, but essentially you try to disrupt your aggregates and measure how many of them are still intact after you make some attempt at disrupting them. So in some cases this is done by putting a soil sample on top of a sieve or a set of sieves and running some water gently but firmly through that soil to see what sieves catch the aggregates. In the case of an experiment that was done in the late 90s at the Central Maryland Research and Education Farm in Clarksville, Dr. Vo and his doctoral student, Dr. Min, actually shook up the soils rather gently and then looked at how much soil was still suspended and took that as the difference between what was aggregates. But anyway, they had a high manure rate, a low manure rate, and a fertilizer control on alfalfa. And they found that there was greater aggregate stability in the high manure rate than there was in the low manure rate. And both of those were better than the control. So again, even using a rather crude technique, we can see that adding manure and adding more manure produces more stable aggregates than commercial fertilizer alone. Okay, now I'm going to switch gears for a moment and talk about the effect of manure on what's considered to be greenhouse gases. There's more and more emphasis across the country and across the world on global warming, and anything that produces greenhouse gases comes under a certain amount of scrutiny. Well, we already know that carbon dioxide is a greenhouse gas, but soils and a soil system are both a source and a sink. And the data out there is pretty chaotic. But we do know that animal production systems can produce methane produced by herbivores, and we do know that methane can be produced in soils under certain circumstances. And in terms of nitrous oxide, we've known for over 100 years that nitrous oxide is produced during the process of denitrification. So agriculture, crop and animal agriculture, certainly have a role in terms of greenhouse gas production, and a number of scientists across our country and across the world have looked at the contribution of crop production and animal production, but that's another seminar, on greenhouse gases. So first of all, understand that methane is much more potent in terms of its effect on trapping heat than carbon dioxide is. It's now agreed that every molecule of methane, CH4, is about 20 times as potent as carbon dioxide in terms of its effect on greenhouse gas, or in terms of global warming and heat retention. And nitrous oxide is even worse. Nitrous oxide is about 300 times as potent per molecule compared to carbon dioxide. Now, you might know nitrous oxide as laughing gas, and I know in the 70s I went to a dentist that actually put a mask on his patients and gave us a little laughing gas during treatment so that we were calmer. I don't know if that's still used in dentistry or not. Anyway, dinitrogen oxide or nitrous oxide is a product of denitrification, and we know they can occur in our soils when they become anaerobic. And it's fair to say that our soils go anaerobic for at least short periods of time during every growing season when we have sustained rainfalls and the soils are anaerobic until they drain thoroughly. So it's fair to assume that it's not just something that happens in wetland soils, it's also something that occurs periodically in crop soils in upland conditions. And hopefully we remember that the organisms that carry out the denitrification are heterotrophic organisms. Most of them are capable of either using oxygen gas as an electron acceptor if the soils are aerobic, or of using nitrate or other things as electron acceptors if the soils go anaerobic. And they use complicated carbon molecules to carry out this reaction, all right? So they do use the oxygen and nitrate as an electron acceptor. They produce nitrous oxide, but they are using the carbon from complicated organic molecules as their energy source while they're doing this. Okay, so I'm going to show you an experiment that was done in Kentucky, and this was done under field conditions, and they did it on the Kreider silt loam, and they were actually interested in looking at whether a whole array of enhanced efficiency fertilizers or additives had an impact on greenhouse gases. But they included a litter treatment in it, and their data is beautiful, and it's recent, so we are going to talk about it. Now, a few of us went to a field day out at USDA in Beltsville last August, and we saw their apparatus for measuring nitrogen oxides and methane and all kinds of greenhouse gases. But essentially what you do is, after your crop is established, you put a frame in, and then periodically you come back and you put some kind of a structure over that frame, and when you're going to take your measurements, you actually cover it. And your cover has a septum in it, a rubber septum, that allows you to extract a sample of the gas after you've allowed your system to close up for an hour or two, however long your experimental protocol calls for, so that you can get the buildup of gases underneath. So in this particular experiment, all of the nitrogen sources were added at 150 pounds of nitrogen per acre. They had urea and ammonium nitrate as in there, but they also had some urease and nitrification inhibitors and a polymer-coated nitrogen source, as well as poultry litter. And during the growing season, they actually went out and extracted the gas from the chambers 2 to 3 times per week. So they have data from the entire season, and we're just going to look at 1 or 2 graphs from that. So this is the table that shows the cumulative nitrate flux measured in kilograms of nitrogen per hectare given off over the season. And again, here's Super U. This is a urease and nitrification inhibitor. Here's agrotane. Here's ESN. That's a polymer-coated urea. And then we've got urea, ammonium nitrogen. You've got poultry litter with agrotane, and finally the control. And these numbers indicate if the numbers are the same, it means they're not different statistically, and if they're different, they are statistically different. So you can see that the poultry litter treatments had far more nitrous oxide given off over the season than any of the commercial nitrogen, whether they were enhanced efficiency. The control was different than only the environmentally, the ESN, not different than the ones that had the nitrification inhibitors and the urease inhibitors. But there's a clear difference between all the nitrogen fertilizers and the control and the litter treatments. And now one of the ways they looked at whether the effect was how much nitrogen oxide was actually exuded into the system or released into the atmosphere per bushel of product, which is a kind of a helpful way of looking at it. Now this is kind of a mishmash unit. It's grams of nitrogen gas per bushels, but when I looked at the different ways of converting what they published, this was the one that made the most sense to me. So you can see that for all these special products or additives, there's a modest amount of nitrogen given off in the form of nitrous oxide per bushel of product. In the case of control, there was still some from the nitrogen that was in the system, right? But the amount of nitrogen that was given off as a greenhouse gas, nitrous oxide per bushel, for the litters, regardless of whether the litter was treated with a nitrification and urease inhibitor or not, is substantially higher. And the 2 arrows mean that they were significantly higher than all the other treatments. And from a statistical point of view, those other treatments, both the control and the inorganic nitrogen ones, with or without enhancing products, were not significantly different. So hopefully we understand why this happens. Again, those organisms are heterotrophs. They live on complex organic molecules, and the litter supplied not only the same amount of nitrogen as the other treatments, but it also supplied a very labile, think digestible, source of carbon. So when the soils went anaerobic during the season, The heterotrophs were able to get more work done, more denitrification, when they had a labile source of carbon than when they did not. Now, this is not at all surprising because people studying denitrification losses have been finding this on many locations across the country for at least the past 15 years when gas chromatographs became more available and occurred in more soils labs. So this is no surprise. This experiment did look at the newer products, the newer additives, so it's the first time we've really seen some good data on that published in the peer-reviewed literature. I will say that there were no differences in methane as affected by nitrogen sources. The big effect here was on the nitrous oxide produced through the denitrification process. And you wouldn't really expect a whole lot of methane production unless you're so anaerobic for a long period of time, because it takes a much deeper anaerobic condition for methane to be produced than it does for nitrous oxides. Okay.
Trish, we did have a question come in from Craig. He wondered if that litter was incorporated.
I'd have to go back and look. I don't remember offhand. If you want, I'll send you the whole study. And that's true of any of you if you want to read some of this stuff. Okay, so let's talk for a minute about veterinary pharmaceuticals, because there's more and more concern about the antibiotics and the ionophores that are used in animal production. And I think that's coming up on lots of radar screens, and I want you to at least be aware of it. Well, first of all, there's two terms. Antibiotics is a term that in most people's mind is very general, but in fact most of them are actually antibacterials. And that's true of the stuff that's used in the human population too. Streptomycin isn't an antiviral, it's an antibacterial, right? And the same is true for many of the materials used in animal production. And the interesting thing is that there's many antibiotics that are used both in veterinary medicine and in human disease treatment, the same actual materials. Then there's another group of materials out there called ionophores, and those essentially are antibiotics, though they're often much more narrow spectrum, and they are used only in animals. Okay? So you might see signs in food in the grocery store that says no antibiotics were used in the production of this food, but chances are some ionophores were used. Right? Now the concern is that these materials might pass through the animal unmetabolized. And this shouldn't surprise us because the data on the human population in terms of the various pharmaceuticals human beings take shows that some of them are metabolized almost completely and others are only metabolized to 50% or 10% or 5%. So realize that when you take a pharmaceutical, a lot of it might come out in your urine or your feces also. It's not uncommon for substantial portions of these materials to pass through the animal unmetabolized. Right? So there's a concern of, well, does it affect the soil organisms? Well, if it's an antibiotic, it certainly can affect the soil organisms. It can shift populations, favor some over others. It could cause resistance among organisms over time. There certainly are some concerns about that. And then, of course, there's concerns about whether or not those materials are taken up by plants, whether or not they're taken up in high enough amounts to impact people negatively. So there's a whole array of concerns by various professionals out there about the use of veterinary antibiotics. Okay? So be aware of the fact that there are two measurements out there used in this literature. One is the average daily intake, and this looks at how much of these materials would be taken in per day at a level where it would cause problems. And then there's another thing called the maximum residue level, and this is the maximum amount of an antibiotic or another food additive that is considered safe. All right, above that, you might be running into issues. And there is a group, this is an international group, it's the Joint Committee on Food Additives, the Joint Expert Committee on Food Additives. It's a group of scientists that were impaneled by the Food and Agricultural Organization of the UN, and they basically have gathered data and established maximum residue levels and average daily intakes. The average daily intakes were only established for animal products, meat and milk and eggs and things like that, not plant products. And the greater emphasis was put on the amount that would trigger an allergic reaction in someone who was allergic to the antibiotic. So the rationale behind average daily intakes is what's the amount that would be safe for someone to consume in the food they ate per day if they were allergic to, let's say, penicillin or amoxicillin, okay? And they also looked, but this was to a lesser extent because it's much harder to do, what's the amount people could ingest every day all their life and not have any health risks. So they certainly want the amount that we would consume in our food to be less than would trigger allergic reactions and less than that would cause long-term lifetime health risks, kind of like the MCL in water. Right? Okay. So there's a group of scientists in Minnesota that have done a huge amount of work at this. They're at the University of Minnesota. And here's just one study they looked at. They looked at an antibiotic called sulfamethazine. And this came up on their radar compared to others that they could have looked at because sulfamethazine is one of the most widespread antibiotics in animal production. It's used in cattle production. It's used in swine production. So in terms of the tonnage that's used a year, there's actually 400 tons of this stuff used per year in animal production in the United States alone. Now, in addition to that, it's a rather small molecule, which means there's a greater tendency that it might pass the root membrane. And it's known to be, have a very low adsorption capacity to soil. So it's small, it stays in the soil solution, and it's used in large quantities. So in a greenhouse environment, they looked at 3 crops, corn, lettuce, and tomatoes. And in the first phase of this, they looked at just regular swine manure from a commercial swine operation with the normal amount of sulfamethazine that was used by that producer. And sure enough, they found that sulfamethazine was taken up by these crops. So their second question was, well, okay, if there's more in the soil, will the plants take up more, or is there just kind of a cap regardless? And so this was a greenhouse experiment where they spiked manures with 2 levels of sulfamethazine, 50 milligrams per liter of manure and 100 milligrams per liter. And sure enough, they found that there tended to be more taken up if there was more in the soil. Okay? They also showed that there are certainly some very significant differences. Lettuce took up more than the potato did, and potato took up more than corn. So this showed that number one, sulfamethazine was taken up by the plants. That is, this small molecule that stays out in the soil solution is able to pass through the root membrane, and that the more that is there, the more it could take up. Although realize that this difference in lettuce is not significant. These are both Bs, while the difference in potatoes was. There was significantly more of this antibiotic taken up at the 100 milligram per liter application rate than the 50. Is this used in humans? Yes. It is used in humans. And yes, it is used for urinary tract infections. So this is an example of an antibiotic that is used both in the human population and in veterinary medicine. Okay, so to go back to the maximum residue level in animal products, it's only considered safe to have 1/10 of a milligram per kilogram of fresh weight. Okay, so remember there are no standards set for plant products. So they looked at the 3 vegetables, and the average was 0.05 milligrams per kilogram of stuff. So it's well below what would be the animal norms, okay? And we also, if we look at the average daily intake of sulfamethazine, it's considered that you could take in 5 milligrams per kilograms of your body weight per day, and they ran through some typical diets, and they found that even with a vegetable-based diet at these rates, the daily intake would not exceed the ADI, or the average dose that's considered to be safe. Okay, now remember that these levels are set so that it should not trigger an allergic reaction in an allergic person. There are many, many of us out there that are allergic to sulfa drugs, myself included, and this is one of those in that group. But these levels are set to be protective of people who have allergic reactions. Now, I am not an expert in that field. I cannot speak to how this was done, but I can say that a worldwide panel of experts was impaneled to look at these issues. So if we want to know more about that, we're going to have to find some other speakers, okay? Okay, well, let's go back to this for just a moment. There are many, many antibiotics out there. Some are taken up, some are not. Some are large enough or have a chemical structure such that they cannot pass the root membrane. Others of them are taken up. There are various chemistries among medications, just like there are various chemistries among herbicides. So this is just one example of a medication that is used both in the human population and the animal population, right, that is taken up by the roots. And the reason this is important, because for a number of years, if you had articles about, oh, well, don't worry about the antibiotics in manure, because they'll never pass through the root membrane, okay? That was before anybody bothered to look. Once they actually bothered to look, they found out that some are taken up while others are not, right? So don't be alarmist about it. Okay, let's look at a little herbicide carryover, because this is a very interesting story. Manure can contain active ingredients from herbicides that were put on the crops grown in the fields where the manure was applied. Okay? And the big daddy here are things that belong to the pyridine, carboxylic acid family. So it's things like chlorpyrrolid, picorin, fluoxapore, and triclopor. They are known by trade names such as Stinger, Reclaim, Forefront, and Milestone. Okay? They're used for broadleaf weed control in pastures, hay, fields, and golf courses. And until about 2000, they were also labeled to use on home lawns. They were pulled by the manufacturer early in this century when a number of composting, commercial household grass leaf composting facilities crashed, basically, because grass clippings from treated lawns produced toxic composts. Okay? So after that became known in the late 1990s, the manufacturers voluntarily changed the label to exclude use on home lawns. So it's no longer labeled for home lawns, but it is labeled for golf courses and commercial lawns. This material is not metabolized by the herbivores. It's even safe for dairy cows to use. It just passes right through them. It's excreted in the manure, primarily in the urine. Okay? It's not readily altered by composting. Right? So whether it got in there because of manure that was applied, or whether it got in there because of lawn clippings that were put into a composting facility, it is not altered by composting. Right? It takes a long time to break down under any conditions, and some studies show that a year of composting doesn't change it. I don't know how much composting would change it, but that's as far out as that particular study was run. Okay? So, clippings from treated lawns, as I said, caused essentially hundreds of tons of unusable compost to be produced at least 4 major cities that I know of. The composting industry, the commercial composting industry, like the United States Composting Council, is absolutely up in arms about the use of these materials. If they had their say, these would be yanked off the market. It turns out they were approved in a program to find, an EPA program to find some less toxic herbicide alternatives, so it's kind of an ironic story. Certainly manure from animals either fed hay or grazed on pastures with these treatments should never be used on a field where broadleafs are being grown. It should only be used on fields that have grass-like crops. These chemicals are auxin-like. They mimic the activity of growth stimulants, and they cause severe deformation, stunting, and death of the plants. And if you want to know a really interesting scenario about this, you've got to talk to Tricia Hoops or the home gardening coordinator in Harford County, because there's a very interesting story of them using some horse manure compost on some demonstration gardens at the Ripken Stadium and finding results like this. But eventually, many of the crops actually died. This is a photo from an Oregon State Extension website. Okay? So the advice now, even on the label for these products, is don't let your animals graze on areas other than grass. If hay is produced on these fields, alert the people who might be buying it of the concerns. The label on all of these products has been greatly enhanced about the dangers of using it on broadleaf crops since these problems came to light. Okay, so we talked about a lot of very different aspects of manure utilization, from its effect on physical and biological properties to greenhouse gases to antibiotics through herbicide carryover. So I think we'll open it now for some questions.